Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to rest. Tonight we're drifting into something a little quieter, a little farther away, and perhaps a little colder than anything we usually experience. Not just a winter morning kind of cold, or the kind that makes you pull your blanket a bit tighter, but something much deeper, something that stretches across the entire universe. Because out there, beyond the warmth of sunlight and the comfort of air, space waits in a kind of stillness that doesn't quite behave the way we expect. It doesn't shiver, it doesn't blow like wind, and it doesn't bite like frost. And yet, we often hear it described with a single simple word: cold. But what does that actually mean? Before we gently unpack that idea, I'd like to ask you something, just as a way of settling in. Where in the world are you listening from right now? And more curiously, what does the temperature feel like where you are? Maybe it's warm and comfortable, or maybe it's a little chilly, the kind that makes your hands instinctively tuck into your sleeves. It's interesting, isn't it? How quickly we become aware of temperature when it changes, and how much it shapes the moment we're in. If you find this kind of slow exploration calming, or simply a nice way to wind down after a long day, I'd be quietly grateful if you gave the video a like and maybe subscribed. It helps this small, peaceful corner reach others who might need a gentle pause too. Now let's ease into it. When most people think about space, they imagine it as extremely cold. The kind of cold where things freeze instantly, where breath turns to ice, and where anything warm simply cannot survive. It's a very common picture, and it's not entirely wrong, but it is in a way incomplete. Because space is not cold in the way your freezer is cold. It's not even cold in the way a winter night is cold. In fact, one of the first surprising things about space is that it doesn't really have temperature in the way we experience it here on Earth. And that's where things begin to get interesting. You see, here on Earth, temperature is something we feel constantly, even when we're not paying attention to it. The air around you is always interacting with your body, gently exchanging heat. If the air is cooler than your skin, heat flows outward and you feel cold. If the air is warmer, heat flows inward and you feel warm. It's a continuous conversation, happening quietly and automatically. But space doesn't participate in that conversation. There's no air out there, no breeze, no invisible ocean of molecules bumping into your skin. Just vast emptiness, stretching in all directions. And without that constant exchange, the idea of cold becomes something very different. To understand why, it helps to think about what temperature actually is. Not in a complicated, equation-filled way, but in a simple, almost everyday sense. Temperature is really just a measure of how much energy something has, specifically, how much the tiny particles inside it are moving. When something is warm, its particles are moving more energetically, vibrating, colliding, shifting around. When something is cold, those movements slow down. Less motion, less energy, lower temperature. Here on Earth, everything is full of particles. The air, the ground, the objects around you, even the glass of water sitting nearby. So, temperature is easy to measure, easy to feel, and constantly shared between things. But in space, there are almost no particles at all. It's not completely empty, but it's very close. In some regions, you might find just a few atoms scattered across an area the size of a room, or even larger. And with so little matter around, there's very little to carry heat, very little to transfer it, and very little to define what temperature even means in a practical sense. So when we say space is cold, we're really talking about something more subtle. We're talking about what happens when there's almost nothing left to hold heat. If you were to place an object in space, something warm like a cup of tea, it wouldn't immediately freeze. Instead, it would slowly lose its heat, radiating it away as invisible energy, spreading out into the emptiness. There's no air to pull the heat away quickly, no wind to speed up the process, just a gradual quiet release. And that slowness is important. It means that space isn't aggressively cold. It doesn't actively freeze things the way we might imagine. Instead, it simply allows heat to drift away, with nothing to stop it. In a way, it's less like being plunged into ice, and more like being left alone in a place where warmth has nowhere to stay. Now, there's another layer to this, one that makes space even more fascinating. Even though space is mostly empty, it isn't completely without energy. In fact, the entire universe is filled with a faint, almost ghost-like glow, something called the cosmic microwave background. It's a kind of leftover warmth from the very early universe, a quiet echo of the moment everything began. This background has a temperature about 2.7 degrees above absolute zero, which is incredibly cold by any standard we're used to. But it's also incredibly gentle. It doesn't feel like anything, because it's so faint, so spread out. Still, it gives us a kind of baseline, a way of saying, if you go far enough from stars, far enough from galaxies, far enough from anything that produces heat, this is what remains. A kind of universal chill, not harsh, not biting, just quietly present. And yet, space is full of contrasts. Because while some regions are incredibly cold, others can be intensely hot. If you're in direct sunlight, even in space, you can feel heat building rapidly. Without an atmosphere to scatter or soften the light, the sun's energy arrives directly, strongly, and without much interference. So, in space, you can have situations where one side of an object is extremely hot, while the other side, facing away from the sun, is extremely cold. There's no air to balance things out, no gentle blending of temperatures, just sharp differences side by side. It's a strange kind of environment, one that doesn't behave the way our everyday experience prepares us for, and perhaps that's part of what makes it so intriguing. We tend to think of cold as something that surrounds us, something we step into or escape from. But in space, cold is more like an absence of interaction, an absence of energy being shared. It's not that space is actively cold, it's that it doesn't hold on to warmth. If you imagine sitting in a quiet room with no sound at all, not even the faintest hum, that silence might feel unusual at first. Not because something is happening, but because something is missing. Space is a bit like that, but with heat. It's not that cold is pressing in, it's that warmth has nothing to stay with. As simple as the question sounds, how cold is space, really? The answer turns out to be layered, a little surprising, and at times even counterintuitive. And once you begin to see it that way, space becomes less like a hostile, frozen void, and more like a quiet, patient environment, one that simply follows its own rules. If you pause for a moment and think about the last time you felt truly cold, it probably involves something very familiar. Maybe stepping outside on a winter morning, that immediate sharpness in the air, or touching something icy, where the chill seems to rush straight into your fingers. There's usually a clear sensation, something almost active, as if the cold is reaching out toward you. But that feeling, as real and immediate as it is, depends on something we rarely notice. It depends on air. Here on Earth, cold is not just a temperature. It's an experience shaped by constant interaction. The air around you is always in motion, always brushing against your skin, always carrying heat away or bringing it in. Even when it feels still, there are countless tiny molecules moving, colliding, exchanging energy with everything they touch. When you feel cold outside, what you're really experiencing is heat leaving your body. The air is cooler than your skin, so energy flows outward. The faster that heat is carried away, the colder you feel. That's why wind makes everything feel colder. Not because the air itself is drastically different, but because it speeds up that heat loss. It keeps replacing the thin layer of slightly warmed air around your body with fresh, cooler air, pulling heat away more efficiently. It's also why water feels colder than air at the same temperature. Water is much better at transferring heat, so it draws warmth from your body faster. Step into cold water, and the sensation is immediate, intense, almost overwhelming. So, in a very real sense, cold on Earth is not just about temperature. It's about how quickly your body is losing heat. Now, take all of that, the air, the wind, the constant flow of molecules, and remove it completely. That's space. There's no breeze, no invisible layer of air touching your skin, no medium to carry heat away quickly. Just emptiness, stretching in every direction. And without that medium, the entire experience of cold changes in a way that's surprisingly gentle, at least at first. If you could somehow stand in space, ignoring for a moment all the other problems that would come with it, you wouldn't feel that immediate biting cold we're used to. There would be no sharp sensation rushing across your skin, no wind chill, no icy air pressing against you, because there's nothing there to touch you. Instead, the only way your body would lose heat is through radiation. That means your body would slowly emit energy in the form of infrared radiation, like a very quiet glow that carries warmth away into the surrounding emptiness. And slowly is the key word here. Compared to the rapid heat loss we experience in air or water, radiative cooling is much more gradual. It doesn't pull heat away in a rush, it lets it drift away, quietly, steadily, without urgency. So, paradoxically, space doesn't feel aggressively cold. It feels more like a place where warmth simply fades. This difference is subtle, but important. On Earth, cold feels like something happening to you. In space, it's more like something slowly stopping. Another way to think about it is to imagine sitting in a perfectly insulated room. No drafts, no airflow, no contact with anything cooler than your body. At first, you'd feel quite comfortable, because your body heat would remain close to you, not being carried away. In space, there's no room at all, but the principle is similar. Without air, there's no efficient way for heat to leave quickly. Of course, over time, that heat would still be lost. Radiation would continue, and eventually you would cool down. But it wouldn't be the sudden, dramatic freezing that we often imagine. This is one of the biggest misconceptions about space, the idea that you would instantly turn to ice. It's an image that appears often in movies and stories, but it doesn't quite match the physics. Instead, the process is quieter, more gradual, more patient. Now there's another piece to this puzzle, and it has to do with how our bodies interpret temperature in the first place. The sensation of cold isn't just about how much heat we're losing. It's also about how our skin and nerves respond to changes. Our bodies are very sensitive to rapid shifts in temperature, especially when they involve direct contact. Touch something cold, and your skin reacts immediately. The sudden transfer of heat triggers nerve signals, and your brain interprets that as cold. But in space, without that direct contact, those signals would be very different. There's no surface pressing against your skin, no stream of cooler molecules brushing past. So the usual triggers for that sharp, cold feeling are missing. In a strange way, it's possible to be in an environment that is extremely cold by measurement, and yet not feel cold in the way we expect, at least not right away. That disconnect between measurement and sensation is part of what makes space so unusual. Because when we say space is cold, we're often referring to numbers, temperatures measured in degrees, values that describe the average energy of particles in a region. But our bodies don't experience numbers, they experience interactions, and in space, interactions are rare. This brings us to an interesting point. On Earth, temperature is something shared. It's something that moves between objects, equalizing over time. A hot object cools down, a cold object warms up, until they reach a balance. In space, that process is much slower, because there's so little to facilitate it. Objects can remain at very different temperatures depending on their exposure to heat sources like the sun. For example, something in direct sunlight can become quite warm, even hot, because it's absorbing energy continuously. But if that same object rotates or moves into shadow, it can begin to cool rapidly, losing heat through radiation. Without air to distribute heat evenly, these differences can be extreme. This is why astronauts and spacecraft have to be designed very carefully. Not just to deal with cold, but to manage both extremes at once. Too much heat on one side, too little on the other. And all of this comes back to that simple idea. Cold in space feels different because the mechanism is different. On Earth, cold is carried to you. In space, heat leaves you. One is active, the other passive. One surrounds, the other empties. And once you start to see that distinction, the image of space begins to shift. It's no longer just a frozen void, but a place where temperature behaves in a quieter, less intuitive way. There's a very familiar image that tends to appear whenever space is mentioned in films or stories. Someone is suddenly exposed to the vacuum, and within seconds, sometimes even less, they freeze solid. Their body stiffens, ice forms instantly, and everything stops as if time itself decided to pause. It's dramatic, it's memorable, and in a quiet, cinematic way it makes sense to us. After all, if space is extremely cold, then surely freezing would happen immediately. But this is where intuition gently leads us in the wrong direction, because the idea of freezing instantly depends on something we've already begun to uncover. It depends on how heat leaves the body, and in space, that process doesn't behave the way our instincts expect. To understand why, it helps to revisit something simple. Freezing, in the everyday sense, happens when heat is removed quickly enough for liquids to solidify. Water turns to ice when its temperature drops below a certain point, but getting there requires energy to be carried away. On Earth, that's relatively easy. Cold air, cold surfaces, or cold water can pull heat out of something rapidly. The more efficient the transfer, the faster freezing happens. Put a bottle of water in a freezer, and the cold air continuously absorbs heat from it. The process isn't instant, but it's steady and efficient. The freezer is actively taking heat away. Now imagine placing that same bottle in space. There's no cold air surrounding it, no molecules brushing against it, pulling energy away, just empty space offering no direct contact at all. So instead of rapidly freezing, the bottle would begin to lose heat slowly, by radiation alone. It would cool down, yes, but not in a sudden, dramatic way. More like a quiet release, as warmth gradually drifts away into the surrounding void. And the same principle applies to the human body. If someone were exposed to space, ignoring for a moment the many other serious effects that would occur, they wouldn't instantly turn into a frozen statue. Their body heat wouldn't vanish in a flash. Instead, it would begin to fade. Gently at first, then steadily, but not explosively, not all at once. This is where the illusion comes from. We tend to associate cold with speed, because on Earth, cold environments often remove heat quickly. But space is not efficient at doing that. It's vast, it's empty, and because of that, it's surprisingly slow at taking heat away. There's also another detail that often gets overlooked. The human body is mostly water, and water has a high heat capacity. That means it holds onto heat quite well. It doesn't change temperature instantly. It resists sudden shifts, taking time to warm up or cool down. So even in an environment as extreme as space, the body would not freeze immediately. It would take time for enough heat to leave for freezing to occur. In fact, something else would happen first, something that might seem even more surprising. Without pressure, the liquids in the body would begin to behave differently. Water doesn't just freeze when conditions change, it can also boil. And in the vacuum of space, where pressure is almost non-existent, the boiling point of water drops dramatically. This means that exposed moisture like saliva or the thin layer of liquid on the surface of your eyes could begin to boil, not because it's hot, but because the pressure is so low. It's a strange thought. Boiling and freezing, both connected to the same environment, but it highlights just how different space really is from anything we experience on Earth. And again, this happens gradually, not as a sudden transformation, but as a process unfolding over time. There's also the matter of heat already present in the body. Even without external sources of warmth, the body contains stored energy. Muscles, tissues and organs all hold heat, and that heat doesn't disappear instantly. It radiates outward, slowly, quietly, without urgency. If you imagine holding a warm cup in a still room and then placing it down and leaving it untouched, it cools over time. It doesn't snap into coldness, it drifts there. Space is more like that room, but without walls, without air, without anything to speed the process along. Now, of course, none of this means that space is safe or gentle. The absence of pressure, the lack of oxygen, and the extreme environment would cause serious effects very quickly, but those effects are not the same as instant freezing. The freezing itself would be a slower, secondary process, and that distinction matters because it changes how we understand the environment. It shifts space from something that violently freezes everything in its path to something more indifferent, something that doesn't actively act upon you, but simply allows physical processes to unfold in their own time. There's a certain quietness to it. No rushing wind, no biting chill, no sudden crystallization. Just a gradual loss. Another way to look at it is this. On Earth, freezing often feels like something happening to an object. In space, it's more like something stopping. Heat leaving, motion slowing, energy dissipating. It's less dramatic, but in a way more profound. Because it reminds us that temperature is not just about how cold a place is, but about how energy moves within it, and in space, energy moves differently. This also explains why spacecraft don't instantly freeze solid when they travel through space. If that were the case, building and maintaining satellites, telescopes, or space stations would be nearly impossible. Instead, engineers design systems to manage heat carefully, not because it disappears instantly, but because it doesn't. Heat can linger, accumulate, or escape unevenly, depending on the situation. So rather than protecting against sudden freezing, they're balancing a delicate exchange, making sure that heat neither builds up too much nor drifts away too slowly. And that balance is one of the quiet challenges of working in space. Not a place of instant transformation, but one of gradual shifts. Not a sudden freeze, but a slow release of warmth into an endless background. And once that idea takes hold, it opens the door to a deeper question. If freezing isn't the immediate outcome we imagined, then what exactly is temperature in a place like space? What does it really mean to say something is cold when there's almost nothing there to measure it against? Now, before we move any further into space itself, it helps to pause and take a closer look at something we've been using this whole time without really questioning it. Temperature. It's one of those words that feels so familiar, so immediate, that we rarely stop to ask what it actually represents. You check it on your phone before going outside, you adjust it slightly when making tea, you might even feel it instinctively without needing any numbers at all. Warm, cool, cold, hot. These are experiences we've had since the very beginning, long before we learned to measure them. But the way temperature feels, and what temperature actually is, are not quite the same thing. And this difference becomes especially important when we start talking about space. Because out there, temperature behaves in ways that don't match our everyday expectations. So let's slow this down and look at it from the ground up. At its core, temperature is not really about how something feels. It's about how much energy is present in a system. More specifically, it's about the average energy of motion of the particles inside something. Every object, whether it's a cup of tea, a rock, or a distant cloud of gas, is made up of tiny particles, atoms and molecules that are constantly moving, vibrating, colliding with one another. When those particles are moving quickly, we say the object has a higher temperature. When they're moving more slowly, we say it has a lower temperature, that's it. Temperature is, in a very real sense, a measure of motion. Now here's where it gets interesting. This definition works beautifully for things that actually contain particles, things like air, water, or solid objects. But what happens when there are almost no particles at all? What happens when you're dealing with space? This is where the word temperature starts to become a little less intuitive. Because if temperature depends on particle motion, then in a region with very few particles, what exactly are we measuring? Imagine a vast empty room. Not just empty in the everyday sense, but almost completely devoid of matter. Maybe a few atoms scattered here and there, drifting slowly, barely interacting. If you tried to measure the temperature of that room, you could assign a number to it, based on the energy of those few particles. But would that number mean the same thing as the temperature of air in your living room? Not really. Because in your living room, temperature reflects billions upon billions of particles interacting constantly. It's dense, it's active, it's something your body can feel. In that nearly empty room, the number would describe something much more abstract. A kind of average of very few interactions, and that's essentially what space is like. When scientists say that deep space has a temperature of about 2.7 degrees above absolute zero, they're referring to the energy of the few particles and radiation that exist there. It's a meaningful measurement in physics, but it doesn't translate directly into a physical sensation. Your body wouldn't feel 2.7 degrees above absolute zero in the way it feels cold air on a winter day. Because again, there's nothing there to carry that temperature to you. This is one of the key ideas to settle into. Temperature is not something that exists independently of matter. It's a property of matter. It describes how energetic particles are, but it doesn't move or act on its own. What we experience as heat or cold is not temperature itself, but the transfer of energy. When you touch something hot, energy flows into your skin. When you touch something cold, energy flows out of your skin. Your nerves detect that flow, and your brain interprets it as temperature. So in a sense, we don't feel temperature directly. We feel the movement of energy. And this distinction becomes very important in space. Because in space, even if something has a very low temperature, there's no efficient way for that low energy state to affect you. There's no medium to transfer energy quickly. No stream of particles carrying that coldness toward you. So while space can be described as extremely cold in terms of particle energy, it doesn't feel cold in the way we expect. It doesn't rush toward you. It doesn't surround you. It simply exists. Now, there's another subtle point here, one that often gets overlooked. Temperature is an average. That means it doesn't tell you about individual particles, but about the overall behavior of many particles together. In a dense system, like air or water, this average is very stable and meaningful. But in a sparse system, like space, the concept becomes a bit less grounded. You might have a few particles moving slowly, a few moving more quickly, and the average gives you a number. But with so few particles, that number doesn't carry the same weight as it would in a dense environment. It's a bit like trying to determine the average mood of a crowd when there are only 2 people in the room. The number might be technically correct, but it doesn't tell you much about the experience. And again, this is why space challenges our intuition. We're used to thinking of temperature as something that defines an environment, but in space, temperature is more like a property of isolated particles and radiation, not something that fills the environment in a tangible way. This also explains why objects in space can have very different temperatures depending on their situation. If an object is exposed to sunlight, it absorbs energy and warms up. If it's in shadow, it radiates energy away and cools down. Without air to distribute heat evenly, these differences can become quite extreme. 2 objects floating close to each other in space can have very different temperatures simply because one is facing the sun and the other is not. On Earth, that kind of difference would quickly even out. Air would circulate, heat would spread, and everything would move toward a balance. In space, that balancing mechanism is largely absent, so temperature becomes more localized, more dependent on specific conditions, rather than something shared across an environment. Now, let's take this one step further. There's a limit to how low temperature can go, a point where particle motion is reduced as much as possible. This is called absolute zero, and it represents the lowest possible temperature in the universe. At absolute zero, particles have minimal motion. Not completely still, because quantum mechanics prevents that, but as close to stillness as the laws of physics allow. Space, in its coldest regions, approaches this limit but never quite reaches it. There's always some residual energy, some faint motion, some lingering radiation. So when we say space is cold, we're often comparing it to this lower bound. But again, That comparison is based on measurements, not sensations. Your body doesn't experience absolute zero, it experiences the flow of heat, and in space that flow is slow, uneven, and dependent on context. This brings us back to something we touched on earlier, but now with a clearer perspective. Cold, as we feel it, is not just about low temperature. It's about how quickly energy leaves our body. A cold wind feels colder than still air because it increases heat transfer. Cold water feels colder than cold air because it conducts heat more efficiently. In space, there is no wind, no water, no air. So even though the temperature is extremely low, the rate of heat transfer is also low, and that changes everything. It means that temperature as a number and temperature as an experience can be very different things. One describes the state of particles, the other describes the movement of energy, and in space those two ideas drift apart. As you let that settle in, the question of how cold is space becomes less about a single number and more about understanding the environment itself. It's not just cold in a simple sense. It's an environment where the usual rules of heat and temperature don't apply in the way we expect. Something unusual begins to happen when you remove air from the picture entirely, and it's not always what people expect. Most of what we associate with warmth or cold relies on something we rarely think about. Something that surrounds us constantly and quietly does a tremendous amount of work without ever being noticed. Air is not just something we breathe. It is the main way heat moves around us, the invisible medium that carries energy from one place to another, moment by moment, without pause. On Earth, heat is almost never still. It travels continuously, passing from one object to another, flowing through air, through water, through anything that allows particles to interact. When you step outside on a cold day, the air pulls heat away from your body. When you sit near a heater, warm air transfers energy toward you. Even in a room that feels calm and still, there are countless tiny exchanges happening all the time, collisions and movements that keep energy circulating. Now imagine taking all of that away. No air, no molecules brushing against your skin, no medium to carry heat in or out quickly. That's the conditioned space presence. And once that layer is removed, the entire behavior of heat changes in a way that feels almost counterintuitive at first. To understand this properly, it helps to look at the three main ways heat moves. On Earth, these three methods work together constantly, often without us noticing the differences between them. They are conduction, convection, and radiation. Conduction is the simplest. It happens when two objects touch, and heat flows directly from one to the other. If you place your hand on a cold surface, heat moves from your skin into that surface. The colder the surface, the faster that transfer happens, and the stronger the sensation you feel. Convection is slightly more complex. It involves fluids, like air or water, moving around and carrying heat with them. Warm air rises, cool air sinks, and this movement creates currents that distribute heat throughout an environment. This is why rooms warm up unevenly, why hot air collects near the ceiling, and why a breeze can make you feel colder even if the temperature hasn't changed. Radiation is different. It doesn't require contact or a medium at all. Heat can travel as electromagnetic waves, moving through empty space. The warmth you feel from sunlight is an example of radiation. It crosses the vacuum between the sun and Earth without needing air to carry it. On Earth, all three of these processes are active at once. They overlap, interact, and reinforce each other, creating the temperature experiences we're familiar with. But in space, two of them are almost entirely absent. Conduction requires contact, and in space there's very little to touch. Convection requires a fluid like air, and space has almost none of that. So both of these mechanisms, the ones that dominate our everyday experience of temperature, simply don't operate in the same way out there. What remains is radiation. And radiation, while effective over long distances, is not particularly fast when it comes to cooling objects down. It allows heat to leave, but it does so steadily rather than suddenly. There's no rushing current, no stream of cold particles pulling energy away. This is one of the key reasons why space doesn't behave like a giant freezer. A freezer works because cold air surrounds the object inside it and continuously removes heat through both conduction and convection. The air inside is actively interacting with everything, carrying energy away and maintaining a low temperature environment. In space, there is no such environment. There is no surrounding medium enforcing a uniform temperature. Instead, each object exists more independently, gaining and losing heat based on its own situation. If an object is exposed to a heat source, like the sun, it will absorb energy and warm up. If it is not exposed, it will slowly lose heat through radiation. Without air to mix temperatures together, these conditions can exist side by side without balancing out quickly. This leads to a situation where temperature becomes highly localized. One part of an object can be very warm while another part is very cold, simply because of its orientation relative to a heat source. There's no airflow to even things out, no convection currents to redistribute energy. This is why spacecraft and satellites require careful thermal design. Engineers cannot rely on the environment to regulate temperature. Instead, they must manage heat actively, using reflective surfaces, insulation, and radiators to control how energy is absorbed and released. It's not just about protecting against cold, but also about preventing overheating. Because without air, heat that builds up doesn't easily escape either. If a component generates heat internally, it cannot rely on convection to carry that heat away. It must radiate it out into space, and that process takes time. So in space, heat management is a balance between gaining and losing energy, rather than simply avoiding cold. This brings us to an important shift in perspective. On Earth, we often think of cold as something external, something that surrounds us and actively removes heat. In space, cold is more like the absence of incoming energy. It's what happens when an object is not receiving enough heat to maintain its temperature. The environment itself doesn't enforce coldness in a direct way. It simply allows heat to dissipate without interference. Another way to think about this is to imagine standing in a completely still, insulated environment where nothing is touching you and nothing is moving around you. You would not immediately feel cold because there's no efficient mechanism pulling heat away from your body. Over time, you would cool down, but the process would be gradual. Space is similar, but on a much larger scale. And this leads to an interesting observation. Heat in space is not about what surrounds you, it's about what you're connected to. If you're exposed to a strong heat source, you can become quite warm even in space. If you're isolated from heat sources, you will gradually cool down. The absence of air means that there's no automatic equilibrium, no natural balancing of temperatures across the environment. Everything depends on energy input and output. This is also why the concept of ambient temperature doesn't apply in the same way in space. On Earth, the air defines the ambient temperature. It's the shared environment that everything adjusts to. In space, there is no shared medium in that sense. Temperature becomes a property of individual objects and their interactions with radiation, rather than a uniform condition of the surroundings. Now consider what this means for the human body. Your body constantly generates heat through metabolism. On Earth, that heat is continuously carried away by the surrounding air. In space, without air, that heat would not be removed as efficiently. You would still lose heat through radiation, but not as quickly as through convection. At the same time, if you were exposed to sunlight, you could absorb significant amounts of energy. So instead of instantly freezing, the body would experience a more complex balance of heat gain and loss. This complexity is often overlooked because we tend to simplify space as being uniformly cold. But in reality, it's a place where temperature depends on context, on position, on exposure, and on the mechanisms available for energy transfer. And once air is removed from the equation, everything becomes less intuitive. What feels cold is no longer determined by a surrounding medium. It's determined by how energy flows, or doesn't flow, in a largely empty environment. This shift in understanding opens the door to something even more interesting, because once you realize that heat behaves this way in space, you can begin to see how extreme conditions arise, not just in terms of cold, but in terms of contrast. Environments where one side is heated intensely, while the other side cools steadily. Situations where temperature is not a single value, but a range that depends on orientation and time. And from here, it becomes clearer why space challenges so many of our everyday assumptions. It's not just colder than Earth, it operates under a different set of rules, where the absence of air reshapes how energy moves, how temperature is defined, and how we would experience it if we were there. It might seem like a small detail at first, almost a matter of wording, but saying that space is cold in the usual sense carries an assumption that doesn't quite hold up once you look at it closely. The word itself brings a very specific feeling to mind. Something surrounding you, something pressing in, something that actively pulls warmth away and replaces it with a chill. It's a familiar experience, one we've had countless times, and because of that, it feels natural to extend that idea outward, all the way into space. But the moment you begin to separate sensation from physics, the picture starts to shift. Because in the strictest sense, space is not cold in the way a winter night is cold, or the way ice is cold, or even the way a freezer is cold. Those environments all have something in common. They are filled with matter, filled with particles that can interact, collide, and exchange energy. Space, for the most part, is not. And that difference changes everything. To understand why, it helps to revisit what we mean when we call something cold. On Earth, cold is usually the result of being surrounded by matter at a lower temperature than your body. That matter, whether it's air, water, or a solid surface, comes into contact with you and allows heat to flow outward. This flow is constant, immediate, and noticeable. It's what creates the sensation of cold. It's what makes you pull your hands back when you touch something icy. It's what makes your breath visible on a winter morning. But in space, there is almost nothing to surround you. No air pressing gently against your skin. No current carrying heat away. No continuous interaction with a medium that defines an environment. Instead, there is mostly emptiness. And emptiness by itself does not have temperature in the same way that matter does. This is where the idea begins to feel a little unusual. When we assign a temperature to space, what we're really doing is describing the energy of whatever particles and radiation happen to be present. In deep space, that's often extremely low, close to the faint background energy left over from the early universe. But that number, that measurement, doesn't behave like the temperature of air or water. It doesn't act on you. It doesn't flow toward you. It doesn't surround you in a way that produces a direct sensation. So while it's technically correct to say that space has a very low temperature, it's not accurate to imagine that temperature as something that would feel cold in the usual sense. It's more like a quiet condition than an active one. Another way to approach this is to think about what's missing rather than what's present. On Earth, temperature is shared, it spreads, it moves from one place to another until things reach a balance. That's why a hot cup of tea cools down and a cold object warms up. The environment is constantly interacting with everything within it. In space, that shared environment is absent. Each object exists more independently, gaining and losing heat based on its own circumstances, rather than being forced into a common temperature by its surroundings. If something is exposed to sunlight, it can become warm. If it's in shadow, it can become cold. And these states can exist right next to each other without quickly balancing out. So instead of a uniform coldness filling space, what you have is a lack of uniformity altogether. Temperature becomes local, situational, and dependent on energy input. This leads to a subtle but important realization. Space isn't cold in the way we think of cold environments. It's not a place that actively cools everything down. It's a place where heat is not easily retained unless there is a source providing it. That might sound similar, but the distinction matters. A cold environment removes heat from you. Space allows heat to leave, but doesn't actively pull it away. That difference is tied directly to the absence of air. Air is what makes temperature feel immediate. It's what allows heat to move quickly and continuously. Without it, the process slows down, becoming less noticeable in the short term, even if the long-term outcome is the same. This is why astronauts don't rely on the surrounding space to regulate their temperature. Their suits and spacecraft must create their own controlled environments, because the vacuum outside doesn't provide one. It doesn't help, and it doesn't interfere in the way an atmosphere would. It simply exists. There's also an interesting contrast here when it comes to sunlight. On Earth, sunlight warms the ground and the air, and that warmth spreads. In space, sunlight can heat objects directly, but without air, that heat doesn't spread beyond the surfaces it touches. So an object in direct sunlight can become quite warm, even while the surrounding space is described as extremely cold. At the same time, any part of that object not facing the sun can cool rapidly through radiation, because there's no surrounding medium to slow that process down. This creates sharp contrasts, where temperature differences are not smoothed out by the environment. Again, something that feels very different from what we're used to. All of this points back to a single idea. The word cold carries assumptions that don't fully apply to space. It suggests an active process, a surrounding condition, a shared environment. But space lacks those qualities. It doesn't behave like a cold room or a frozen landscape. It behaves more like an absence of interaction, and once that idea settles in, it becomes easier to see why so many common images of space don't quite match reality. It's not a place where cold rushes in. It's a place where heat slowly fades out. That might seem like a subtle distinction, but it changes how we imagine the environment entirely. Instead of picturing space as something that would immediately freeze anything it touches, it becomes something quieter, something more neutral, where temperature is defined by what's present rather than by a surrounding condition. And that brings us naturally to another question. If space itself doesn't actively impose a temperature in the way we expect, then what provides the baseline? What determines the lowest temperatures we observe in the universe? Long before there were stars, before galaxies had time to gather themselves into spirals and clusters, before anything we might recognize as structure began to take shape, the universe was in a very different state. It wasn't cold. In fact, it was almost the opposite. Everything was packed together, dense and energetic, with temperatures so high that matter as we know it couldn't exist in stable forms. There were no atoms, no solid surfaces, no familiar objects. Just a hot, expanding mixture of energy and particles, moving and interacting in ways that are difficult to picture from where we are now. And yet, despite how distant that era feels, a faint trace of it is still here, not as something dramatic or bright, but as something quiet, something that fills all of space, no matter how empty that space might seem. This is what we call the cosmic microwave background. It sounds technical, but at its core it's simply a leftover glow, a kind of residual warmth that has been travelling through the universe for billions of years, gradually stretching and cooling as space itself expanded. To understand why this matters, especially in the context of how cold space is, it helps to think about what happens when something hot cools down over time. If you heat a piece of metal until it glows and then leave it alone, it doesn't suddenly lose all its heat at once. Instead, it slowly radiates energy away. The glow fades, the temperature drops, and eventually it reaches a point where it no longer emits visible light. But even then, it's not completely without energy. It continues to emit radiation, just at longer wavelengths that we can't see with our eyes. The universe has done something very similar, but on a much larger scale. In its earliest moments, it was incredibly hot and dense. As it expanded, everything began to cool. Light that once had very short wavelengths, high-energy radiation stretched out over time, becoming longer and lower in energy. Today, that same radiation has cooled to just a few degrees above absolute zero, about 2.7 degrees to be more precise, and it fills the entire universe. No matter where you go, no matter how far you travel, this faint background is always there. It doesn't come from any one star or galaxy. It's not produced by anything happening right now. It's simply what remains from a time when everything was much closer together. This is important because it gives us a kind of baseline. Even in the emptiest regions of space, where there are almost no particles, no stars, and no nearby sources of heat, this background radiation is still present. It provides a minimum level of energy, a kind of quiet floor, below which temperatures don't naturally fall. So when we say that space is extremely cold, we're often referring to this value, not absolute zero, but something just above it, defined by this faint, persistent glow. And yet, despite its significance, the cosmic microwave background is incredibly subtle. It doesn't feel warm. It doesn't illuminate anything in a way we can see. It's not something you would notice directly. It's more like a gentle hum than a visible light. A presence that's measurable, detectable with sensitive instruments, but otherwise hidden from everyday experience. This is another reminder of how different space is from our usual surroundings. On Earth, warmth is often associated with something obvious. Sunlight on your skin, heat from a fire, the comfort of a warm room. These are direct, noticeable sources of energy. In space, the background warmth is almost imperceptible. It doesn't interact with you in a strong way. It doesn't transfer heat quickly. It simply exists, evenly distributed, filling the vast emptiness with a uniform, low-level energy. And that uniformity is part of what makes it so useful to scientists. Because it's the same in all directions, with only tiny variations, it provides a kind of reference point. A way to understand the large-scale structure of the universe and how it has evolved over time. But for our purposes, the most important thing is what it tells us about temperature. It shows that even in the absence of stars, even in regions that seem completely empty, space is not entirely devoid of energy. There is always something there, even if it's incredibly faint. And that something sets the stage for everything else. It means that when objects in space lose heat, they don't cool into a perfect nothingness. They approach this background level, this quiet, universal temperature that permeates everything. Now, it's worth noting that not all regions of space are at this temperature. Near stars, temperatures can be much higher due to incoming radiation. Inside galaxies, interactions between particles and radiation can create a wide range of conditions. But in the vast spaces between those structures, in the deep intergalactic regions, the cosmic microwave background becomes the dominant factor. It's what remains when everything else is far away. And that makes it a kind of anchor for our understanding of how cold space can get. It also highlights something else. Cold, in the context of space, is not about the presence of something actively removing heat. It's about the absence of strong energy sources combined with the presence of this faint, lingering background. The universe doesn't freeze things in an aggressive way. It simply expands, cools, and leaves behind this subtle trace of its earlier, hotter state. As you consider that, the idea of space as a silent, empty place starts to take on a slightly different tone. It's not completely empty. It's not completely still. There is a kind of quiet activity, a low-level energy that fills everything, even if we don't perceive it directly. And that energy, faint as it is, plays a role in defining the limits of temperature across the cosmos. Picture an object that has been left alone in a very quiet place, with no breeze, no contact, and nothing moving around it at all. Not cold air, not warm air, not even the faintest current. Just stillness. If you were to come back much later, you would notice something subtle but certain. That object would have cooled down. Not suddenly, not dramatically, but gradually. This is the closest everyday starting point to understanding what happens in space, because in space, everything is left alone in a way that we almost never experience on Earth. And yet, even in that stillness, heat does not stay forever. It leaves, slowly, quietly, and without any urgency. To understand how this works, it helps to think about heat not as something that sits still inside an object, but as something that is constantly in motion. Even when something appears completely stable, the energy inside it is always shifting, always moving at a microscopic level. Particles vibrate, molecules rotate, atoms collide, and all of that activity carries energy. That energy does not need a medium to exist, but it does need a way to move outward if it is going to leave. On Earth, we rarely notice this because there are so many pathways for heat to escape. Air carries it away, surfaces absorb it, and everything around us participates in the exchange. It's a busy system, full of interactions. In space, almost all of those pathways disappear. There is no air to carry heat away. There are no surrounding particles constantly brushing against an object. There is no convection, no steady circulation of energy moving through a medium. What remains is one single mechanism: radiation. Radiation is the way heat travels through empty space. It does not require contact or a medium. Instead, energy is emitted in the form of electromagnetic waves, moving outward at the speed of light. Every object with a temperature above absolute zero emits radiation. Even something that feels cold to the touch is still giving off energy, just at wavelengths that we don't see. So in space, when an object begins to cool, it does so by radiating its heat away. But here is the important part. Radiation is not a fast process, especially when compared to conduction or convection. It does not pull heat away aggressively. It allows heat to drift outward, spreading into the vast emptiness. And because space is so empty, that energy has somewhere to go without ever coming back. On Earth, when heat leaves an object, some of it is often reflected or reabsorbed by the environment. Surfaces warm up, air circulates, and energy can return in different forms. There is a kind of ongoing conversation between objects and their surroundings. In space, that conversation is mostly one-sided. Energy leaves, and it keeps going. It doesn't bounce back in any meaningful way. It doesn't build up nearby. It simply spreads out, becoming more diffuse as it travels. This creates a steady, gradual loss of heat over time. If you imagine placing a warm object in space, it would begin radiating energy immediately. The warmer it is, the more energy it emits. As it cools, the rate of emission decreases, slowing the process down further. So the cooling is not only gradual, it becomes progressively slower as the temperature drops. This is very different from what we experience on Earth, where cooling often feels more immediate and consistent because of the constant presence of air or water carrying heat away. In space, the process is more like a slow fading. There is no sharp moment where something suddenly becomes cold. Instead, there is a continuous gentle decline in temperature. Another way to think about it is to imagine sound. In a room filled with air, a sound can be loud, immediate and noticeable. But if you remove the air entirely, there is no medium for sound to travel through. It doesn't carry, it doesn't reach your ears. Heat, in a way, behaves similarly. On Earth, heat is carried by matter, making it feel immediate and present. In space, without that medium, heat can only travel through radiation, which is less direct, less forceful. It's still there, but it doesn't arrive in the same way. This also explains why objects in space can retain heat longer than we might expect, especially if they are not exposed to strong heat sources. Without convection or conduction to speed up the process, the only way to lose energy is through radiation, and that takes time. At the same time, if an object is exposed to a source of heat, like the sun, it can gain energy quickly. Sunlight carries a significant amount of energy, and without an atmosphere to filter or scatter it, that energy arrives directly. So objects in space are constantly balancing two processes, gaining heat from radiation coming in, losing heat through radiation going out. The balance between these two determines the temperature of the object. If more energy is coming in than going out, the object warms up. If more is leaving than arriving, it cools down. And because there is no air to smooth out these differences, the balance can shift dramatically depending on position and orientation. An object facing the sun can become warm, even hot. The same object, if turned away from the sun, can begin to cool, radiating its heat into the darkness. These changes can happen side by side, creating sharp contrasts. This is why temperature in space is not a single, uniform condition. It is something that depends on exposure, on direction, on whether energy is being absorbed or lost. And the loss of heat, the cooling, is always happening in the background, slow, steady, and unavoidable. Now consider what this means over long periods of time. If an object is left in deep space, far from stars and other heat sources, it will continue to radiate its energy away. As it cools, the rate of energy loss decreases, but it never fully stops. Eventually, the object approaches the temperature of the surrounding environment, which, as we've discussed, is defined by the faint background radiation of the universe. But reaching that state takes time, a great deal of time, because the process is not driven by a strong external force, but by the object's own emission of energy. It is self-regulated in a sense, and this gives space a very particular quality. It is not actively cold, it is passively cooling. It does not impose a temperature on objects, it allows them to lose heat until they reach a balance with the faint energy that remains. This distinction may seem subtle, but it changes how we imagine the environment. Instead of thinking of space as something that freezes objects, it becomes more accurate to think of it as something that slowly drains warmth away. Not aggressively, not instantly, but persistently. There is also something interesting about how this process feels, or rather, how it would feel. On Earth, when you lose heat quickly, you feel cold. The rapid transfer of energy triggers your senses, creating a strong immediate reaction. In space, where heat loss is slower, that sensation would be different. There would be no rush of cold air, no sharp change. Instead, the cooling would happen more gradually, less noticeable in the moment. Over time, of course, the effects would become significant, but the process itself would not feel like the sudden freezing we often imagine. It would feel more like a slow fading of warmth. And this brings us back to the central idea. Space does not behave like a cold environment in the usual sense. It behaves like a place where heat has nowhere to stay, where energy leaves, spreads out, and does not return. Not a place of instant extremes, but a place of gradual processes, where temperature is shaped by the quiet movement of energy, rather than by the presence of a surrounding medium. Step into direct sunlight on Earth, and the experience is familiar. There's warmth on your skin, a gentle increase in temperature, and if you stay there long enough, maybe even a bit of discomfort. Move into the shade, and the effect softens. The air still surrounds you, still carries heat, and the difference between sun and shade, while noticeable, is not extreme. Now take that same idea and remove the atmosphere entirely. No air, no scattering of light, no soft blending between warm and cool regions. Just direct sunlight arriving from one direction, uninterrupted, and deep shadow stretching out in the other. This is where things begin to behave in a way that feels almost contradictory. Because in space, an object can be heated intensely and cooled at the same time. Not in a poetic sense, but in a very literal physical way. To understand how that works, it helps to think about sunlight not as something warm in itself, but as a stream of energy. When sunlight reaches an object, it transfers energy to it. The surface absorbs that energy, and its particles begin to move more energetically. That increase in motion is what we measure as a rise in temperature. On Earth, much of that incoming energy is filtered. The atmosphere absorbs, reflects, and scatters sunlight, spreading it out before it reaches the ground. The air then helps distribute that heat, smoothing out differences between surfaces. In space, none of that happens. Sunlight travels directly from the sun to whatever it encounters. There is no filtering, no softening, no redistribution by air. The energy arrives in a concentrated, uninterrupted stream. This means that surfaces exposed to sunlight in space can absorb a great deal of energy very quickly. At the same time, those surfaces are also losing heat. Even while they're being heated by sunlight, they continue to radiate energy outward into space. The two processes happen simultaneously. Energy comes in and energy goes out. The temperature of the object depends on the balance between these two. If more energy is coming in than leaving, the object warms up. If more energy is leaving than coming in, it cools down. This is true everywhere, but in space, the absence of air makes the balance much sharper. On Earth, if one side of an object warms up, the heat spreads. Air carries it away, surfaces conduct it, and the temperature evens out. In space, that smoothing effect is largely absent. So one side of an object can become very warm, while another side remains cold. Imagine a simple object floating in space, with one side facing the sun and the other facing away. The sunlit side absorbs energy continuously, its temperature rising as long as the incoming energy exceeds the energy being radiated away. The shadowed side, however, receives no sunlight at all. It only loses heat through radiation, gradually cooling down. And because there's no air to carry heat from the warm side to the cold side, the difference can become quite extreme. This is not a small variation. It can be the difference between temperatures that would feel hot to the touch and temperatures that are extremely low by comparison. And all of this can exist at the same time on the same object. This is one of the most striking features of space. Temperature is not uniform. It is not shared. It depends entirely on exposure. If you turn the object slowly, different parts take turns absorbing sunlight and radiating heat away. Over time, this can create a kind of cycle, with temperatures rising and falling as surfaces move in and out of direct sunlight. This is something that spacecraft designers have to account for carefully. Satellites and space stations are constantly exposed to cycles of light and shadow as they orbit planets. One moment, they are in direct sunlight, absorbing energy. The next, they are in shadow, losing heat. Without careful design, these temperature changes could damage equipment or disrupt operations, so engineers use materials and systems that manage heat flow. Reflective surfaces reduce the amount of energy absorbed. Insulation slows the loss of heat. Radiators allow excess heat to be released in a controlled way. All of this is necessary because space does not regulate temperature on its own. There is no ambient environment to stabilize conditions. Each object must manage its own energy balance. Now, if you think about what this means from a human perspective, it becomes even more interesting. In space, you could have one side of your body exposed to direct sunlight, absorbing energy and warming up, while the other side, facing away, is losing heat into the darkness. Without air to carry heat across your body, these differences would not even out quickly. You could experience warmth and cooling at the same time, depending on orientation. Again, not in a sudden or dramatic way, but as a result of how energy flows in this environment. This is why the idea of space being simply cold doesn't capture the full picture. It's not just cold, it's a place where heat behaves differently, where energy arrives directly and leaves gradually, where the absence of air creates conditions that allow for extremes to exist side by side. Sunlight in space is not softened or diffused, it is direct and continuous. At the same time, the darkness of space provides no resistance to heat leaving an object, so heating and cooling are always happening together, and the result is a kind of balance that depends entirely on circumstances, position, orientation, exposure. This also helps explain why certain environments like the surface of the Moon show such dramatic temperature differences between day and night. Without an atmosphere to moderate conditions, sunlight heats surfaces during the day, and once the sun sets, those surfaces begin to cool rapidly through radiation. This cycle repeats, creating a pattern of extremes that would be unusual on Earth, but are natural in space. And all of this comes back to a single idea. Space does not provide a uniform temperature. It provides conditions in which temperature is determined locally by the flow of energy in and out of each object. Sunlight brings energy in, radiation carries energy out, and without air to connect everything together, those processes remain separate, creating contrasts that can feel almost paradoxical. Warmth and cold, existing at the same time, not as opposing forces, but as parallel processes. As this becomes clearer, the environment of space starts to feel less like a single, defined condition, and more like a set of interactions, each one shaping temperature in its own way. Step onto the surface of the moon in your mind for a moment, not in a dramatic or cinematic way, but simply as an observer trying to understand what's happening there. No atmosphere, no wind, no clouds, and no sound. Just a still, quiet landscape under an open sky that never turns blue. At first glance, it might seem like a place that would simply be cold, in the same way we often imagine space itself. But the moon tells a slightly different story. It doesn't settle into one temperature. It swings between extremes, and those extremes are not small. During the lunar day, when the sun is shining directly onto the surface, temperatures can rise to around 120 degrees Celsius. That's well above the boiling point of water. The ground, especially the darker regions, absorbs sunlight continuously, and without an atmosphere to filter or scatter that energy, the heating is direct and sustained. Then, when night falls, and the sun is no longer above the horizon, the same surface begins to lose heat. With no air to hold warmth in place, no clouds to reflect energy back down, and no convection to slow the process, the temperature drops. Not just a little. It can fall to around minus 170 degrees Celsius. That's a swing of nearly 300 degrees between day and night. And what makes this even more interesting is how long these periods last. A single day on the moon, from sunrise to sunset, takes about 2 Earth weeks. That means the surface is exposed to continuous sunlight for a very long time, allowing it to heat up gradually and reach those high temperatures. Then, it spends another 2 Earth weeks in darkness, steadily radiating heat away, cooling down until it reaches those extremely low values. So instead of rapid changes like the daily cycle we experience on Earth, the moon undergoes slow, extended periods of heating and cooling. This gives the process a kind of rhythm, one that is very different from what we're used to. On Earth, the presence of an atmosphere plays a crucial role in moderating temperature. Air absorbs heat, stores it, and redistributes it. Oceans do the same on a larger scale, holding on to warmth and releasing it slowly. Clouds reflect sunlight during the day and trap heat at night. Wind moves energy from one region to another, smoothing out differences. All of these mechanisms work together to keep temperatures within a relatively narrow range, at least compared to the moon. On the moon, none of that exists. There is no air to carry heat across the surface, no convection currents to distribute energy, no water to store warmth, no clouds to reflect or trap radiation. Each part of the surface is left to manage its own energy balance. When sunlight is present, it absorbs energy. When sunlight is absent, it loses energy. And because there's no atmosphere to connect these regions, the temperature differences remain sharp. Now, it's also worth noting that the surface of the moon is not uniform. Some areas are darker, some lighter. Some materials absorb more sunlight, while others reflect it. This means that even during the lunar day, temperatures can vary depending on location. Darker regions like the lunar Maria absorb more energy and can become hotter than lighter regions, which reflect more sunlight, so even within the sunlit side there are variations. But the most dramatic difference is between day and night. And this difference highlights something fundamental about how temperature works in space. It's not just about how much energy is present, but about how that energy is managed over time. On the moon, during the long day, energy accumulates. The surface keeps absorbing sunlight, and without an atmosphere to carry that energy away efficiently, it builds up. During the long night, the opposite happens. The surface radiates energy away, and without an atmosphere to slow that loss, it cools steadily. The process is not sudden, it's gradual, but because the periods are so long, the results become extreme. Now, if you imagine standing on the moon, properly protected of course, you wouldn't feel these temperature changes in the same way you would on Earth. Inside a spacesuit, your environment would be carefully controlled. The suit would regulate temperature, managing heat through internal systems that balance energy gain and loss. But outside that suit, the environment would not feel like a cold wind or a warm breeze. There is no air to carry those sensations. Instead, temperature would be something measured, something affecting objects and surfaces, rather than something directly felt through contact with the surrounding medium. The ground beneath you would be hot or cold depending on its exposure to sunlight, but the space around you would remain a vacuum, offering no direct sensation. This again reinforces the idea that temperature in space is not an environmental condition in the usual sense. It's a property of surfaces and objects, determined by how they interact with radiation. Another interesting aspect of the moon is how shadows behave. On Earth, a shadow is usually just a slightly cooler area, because light is scattered by the atmosphere and some energy still reaches into shaded regions. On the moon, shadows are much darker and much colder. Because there's no atmosphere to scatter light, areas in shadow receive almost no direct energy from the sun. They cool down, sometimes reaching very low temperatures, even while nearby surfaces in sunlight remain hot. This creates sharp boundaries between hot and cold regions. Step from sunlight into shadow, and the temperature difference can be significant, not because the environment changes, but because the energy input changes abruptly. Again, no air to smooth things out. This is also why certain areas near the moon's poles, where sunlight never reaches, can remain extremely cold for long periods. These permanently shadowed regions are among the coldest places in the solar system because they never receive direct sunlight and continuously lose heat through radiation. They exist in a kind of long-term balance where incoming energy is minimal and outgoing radiation dominates. All of this makes the moon a useful example. It shows how temperature behaves in an environment without an atmosphere, where radiation is the primary way energy moves. It shows how exposure to sunlight can create heat, and how the absence of that exposure leads to cooling, and it shows how these processes can produce extremes, not because space is aggressively cold, but because there's nothing there to moderate the flow of energy. The moon doesn't freeze instantly. It heats and cools over time, following the same principles we've been exploring: energy in, energy out, absorption and radiation, and the absence of air allowing these processes to unfold without interference. Designing something to survive in space begins with a slightly unexpected problem. It isn't just about keeping things from getting too cold. It's about dealing with the fact that temperature, as we usually understand it, doesn't behave in a stable or predictable way out there. On Earth, if a machine starts to overheat, the surrounding air helps carry that heat away. If something gets too cold, the environment often provides some level of background warmth. There is always a kind of exchange happening, a steady balancing of energy between objects and their surroundings. In space, that balance does not exist in the same form. There is no air to carry heat away, no convection to distribute energy, no shared environment that naturally stabilizes temperature. Instead, every object must manage its own energy, gaining it from radiation and losing it through radiation, with very little in between. For spacecraft, this creates a situation that is not just cold, but highly uneven. One side can be exposed to intense sunlight, absorbing energy continuously. Another side can be facing deep space, losing heat steadily. Internal components can generate heat as they operate, and without air, that heat has nowhere to go unless it is actively managed. So the challenge is not simply to protect against freezing, It is to maintain a controlled balance of energy in an environment where nothing does that for you. This is why spacecraft are designed with thermal control systems, carefully engineered to handle both heat gain and heat loss at the same time. One of the first things you might notice about many spacecraft is their outer surfaces. Often covered in reflective materials, sometimes appearing metallic or even golden, these surfaces are not just for appearance. They are there to control how much energy the spacecraft absorbs. Reflective materials reduce the amount of sunlight that is absorbed, preventing parts of the spacecraft from becoming too hot. At the same time, other areas may be designed to absorb heat when needed, depending on the mission and the conditions the spacecraft will face. This selective approach allows engineers to manage where energy goes. Another important feature is insulation. In space, insulation works a little differently than it does on Earth. Instead of keeping cold air out, it is used to slow the movement of heat within the spacecraft and to reduce the loss of heat to the outside. One common type of insulation used is multi-layer insulation, which consists of many thin layers of reflective material stacked together. These layers reduce the transfer of heat through radiation, helping to maintain stable temperatures inside. It's not about trapping warm air, because there is no air to trap. It's about controlling the flow of energy. Now, while insulation helps slow down heat loss, it doesn't solve everything. Spacecraft also need a way to get rid of excess heat. Inside a spacecraft, electronic systems, instruments, and other components generate heat as they operate. On Earth, that heat would be carried away by air. In space, without convection, that heat would build up unless it is actively removed. This is where radiators come in. Radiators are surfaces designed specifically to emit heat into space. They are often positioned so that they face away from the sun, maximizing their ability to lose energy through radiation. Heat from inside the spacecraft is transferred to these radiators, which then release it outward. In a way, they act like controlled exits for heat, allowing the spacecraft to maintain a balance. So while space slowly drains heat away from objects, spacecraft don't simply rely on that passive process. They guide it, manage it, and use it to their advantage. There is also the issue of internal temperature. Astronauts and sensitive equipment require stable conditions. Too hot, and systems can fail. Too cold, and materials can become brittle or stop functioning properly. So inside the spacecraft, there are systems that regulate temperature more actively. Fluids may be circulated through pipes to transfer heat from one part of the spacecraft to another. Heaters may be used to keep certain components within their operating range. Sensors monitor temperature constantly, allowing adjustments to be made as conditions change. All of this happens in an environment where the outside offers no help. There is no ambient temperature to rely on, no natural equilibrium. Everything must be controlled. Another interesting aspect is how spacecraft deal with the cycles of light and shadow. For spacecraft orbiting a planet, like the International Space Station, there are regular transitions between sunlight and darkness. Each orbit brings periods of heating followed by periods of cooling. These transitions can happen relatively quickly compared to the long cycles on the Moon. So the spacecraft must be designed to handle repeated changes in energy input. Materials are chosen for their ability to withstand these variations. Systems are designed to adjust as conditions change, maintaining stability even as the external environment shifts. Without this careful design, the temperature swings could damage equipment or make conditions unsafe. It's also worth noting that spacecraft do not aim to match the temperature of space. They aim to create their own environment. Inside, conditions are maintained within a narrow range, comfortable for humans or suitable for equipment. Outside, surfaces are designed to manage energy flow in a way that supports that internal stability. So instead of adapting to space, spacecraft shape their own thermal conditions within it. This approach reflects a broader idea we've been building toward. Space does not provide a stable thermal environment. It provides a set of conditions where energy moves in specific ways, primarily through radiation, and where the absence of air removes many of the mechanisms we rely on for temperature regulation. So survival in that environment depends on understanding those rules and designing systems that work with them. It's not about resisting space, it's about working within its constraints. Another detail that often goes unnoticed is how important orientation is. The direction a spacecraft faces can affect how much energy it absorbs from the sun, and how effectively it can radiate heat away. So spacecraft are often oriented carefully, sometimes even rotating to distribute heat more evenly. This is another example of how temperature in space is not fixed, but depends on position and exposure. Everything comes back to that balance. Energy coming in, energy going out, and the absence of air making those processes more direct and less forgiving. If too much energy is absorbed and not enough is released, the spacecraft can overheat. If too much energy is lost and not enough is gained, it can become too cold. So the entire system is designed to keep that balance within a safe range, and it does so continuously, adjusting as conditions change. This careful management allows spacecraft to operate in an environment that, while often described as cold, is actually much more complex. It's not just about low temperatures, it's about controlling energy in a place where the usual pathways are missing. Imagine for a moment removing all the systems that normally protect a human body from its surroundings. No atmosphere, no pressure, no controlled environment, no steady exchange of air or heat, just the body itself, placed into the same conditions we've been exploring. Not as a dramatic scene, not as something sudden or exaggerated, but simply as a process governed by the same physical rules that apply to everything else in space. What would actually happen? The first thing to understand is that space does not act on the body in a single unified way. There isn't one effect that defines the experience. Instead, several processes begin at once, each unfolding according to its own timeline, and importantly, freezing is not the first of those processes. This is where expectations often drift away from reality. Because when we think about space, we tend to imagine cold as the dominant force. But as we've already seen, a cold in space is not something that rushes in or surrounds the body in a direct way. Heat loss happens, but it happens through radiation, and that takes time. So before the body has a chance to cool significantly, other effects begin to take place. One of the most immediate changes is related to pressure. On Earth, the human body exists under a constant atmospheric pressure. It's something we rarely notice, but it plays an important role in how liquids and gases behave inside us. In space, that pressure is essentially gone. Without external pressure, the behavior of fluids changes. Water, for example, does not need to be hot to boil. At very low pressure, the boiling point drops significantly. This means that moisture on the surface of the body, such as saliva or the thin film of liquid in the eyes, can begin to evaporate or even boil gently, not because it's heated, but because the surrounding pressure is too low to keep it in a liquid state. This process is not violent or explosive, but it is noticeable. It's a shift in how the body interacts with its environment. At the same time, the body itself still contains heat. Internal processes continue, at least initially, and that heat does not disappear instantly. As we've discussed, in the absence of air, heat is lost through radiation, which is relatively slow. So while the body is beginning to lose heat, it is not freezing right away. Instead, there is a gradual change. Another important factor is the absence of oxygen, which affects the body more quickly than temperature changes do. Without a supply of oxygen, the body cannot sustain normal function. This becomes the primary concern in such an environment rather than cold. But staying focused on temperature and energy, the key idea is this. The body does not instantly become cold. It begins to lose heat in the same way any object would in space, through radiation. And that process takes time. Now consider how the body normally regulates temperature. On Earth, the body relies on several mechanisms. It can sweat to release heat, increasing evaporation to cool down. It can adjust blood flow, sending more heat to the skin, or conserving it internally. It can shiver to generate heat when needed. All of these processes depend on interaction with the surrounding environment. Sweating relies on air to carry moisture away. Blood flow relies on the environment to either absorb or retain heat. Shivering generates heat, but that heat still needs to be balanced against what is lost. In space, these mechanisms are limited. There is no air to carry away evaporated moisture, so sweating becomes less effective as a cooling method. Heat generated internally remains within the body until it is radiated away, so in a sense the body's ability to regulate temperature is reduced, not because the environment is aggressively cold, but because the pathways for heat exchange are different. This creates a situation where the body's temperature changes are driven primarily by radiation, rather than by convection or conduction. And as we've seen, radiation is a slower process, so the cooling of the body would be gradual. Now there is also the matter of sunlight. If the body is exposed to direct sunlight, it would absorb energy, just like any other object. That could lead to warming on the side facing the sun, while the side facing away continues to lose heat. This creates the possibility of uneven temperature distribution, where different parts of the body experience different rates of heat gain and loss. Again, not something we're used to on Earth, where air helps distribute heat more evenly. So instead of a uniform experience of cold, the body would be subject to a balance of processes, radiating heat away, absorbing energy from sunlight if exposed, and gradually moving toward a new equilibrium based on those factors. It's also important to note that the body has a certain amount of thermal inertia. Because it is mostly water, and because water has a high heat capacity, it resists rapid changes in temperature. It takes time for the body to cool down significantly, even in an environment where heat is being lost. This further reinforces the idea that freezing is not immediate. The body does not instantly match the temperature of its surroundings. It transitions over time. Now, when we think about how this would feel, it becomes a bit more complex. On Earth, we feel cold because of rapid heat loss, because of air or water interacting with our skin. In space, without that interaction, the sensation would be different. There would be no cold wind, no sharp chill. Instead, there would be a lack of that familiar feedback. Temperature changes would still occur, but they would not be accompanied by the same immediate sensory cues. This is another example of how space changes the way we interpret physical conditions. It separates measurement from sensation. The body can be losing heat, but not feeling cold in the way we expect, at least not at first. As time passes, the cumulative effects of heat loss would become more significant. The body would continue to radiate energy, gradually cooling. But again, this is a process, not a moment, not an instant transformation. And this distinction matters because it highlights how much of our intuition about temperature is shaped by our environment. We're used to air, to contact, to rapid heat exchange. Remove those and the experience changes. Space does not freeze the body instantly. It allows the body to lose heat over time, quietly, steadily, without urgency. And alongside that process, other factors, pressure, oxygen, and internal regulation, play a more immediate role in how the body responds. So when we ask what would happen to the human body in space, the answer is not defined by a single effect. It's defined by a combination of processes, each unfolding according to the same principles we've been exploring: heat, energy, and the absence of air. At some point, when we keep following this idea of heat slowly drifting away, there's a natural question that begins to form. If energy keeps leaving, if motion keeps slowing, does it ever stop completely? Is there a point where everything becomes perfectly still? This is where the concept of absolute zero comes in, not as a place you can visit, but as a boundary, a limit that defines just how cold something can possibly be. To approach it gently, it helps to return to something familiar. Temperature, as we've been building toward, is really a measure of motion. The faster particles move, the higher the temperature. The slower they move, the lower the temperature. So if you imagine gradually removing energy from a system, letting it cool more and more, what you're really doing is slowing down that motion. Less vibration, less movement, less activity. And if you continue that process far enough, you arrive at a point where motion is reduced as much as the laws of physics allow. That point is absolute zero. It's defined as 0 Kelvin, which corresponds to minus 273.15 degrees Celsius, a temperature far beyond anything we encounter naturally in everyday life. But what makes absolute zero interesting isn't just the number, it's what it represents. It represents the lowest possible energy state for a system, a condition where particles have minimal motion, where the internal activity of matter is as quiet as it can be. Now, it might be tempting to think of this as complete stillness, a kind of perfect pause, but the reality is a little more subtle. Even at absolute zero, particles do not become completely motionless. Quantum mechanics prevents that. There is always a small amount of residual motion, something known as zero-point energy. So absolute zero is not a complete stop. It's more like a limit you can approach, but never fully reach. And this brings us back to space. Because when we talk about space being cold, we often imagine it as being close to this limit. And in some ways, it is. The cosmic microwave background, which we explored earlier, has a temperature of about 2.7 Kelvin. That's only a few degrees above absolute zero. In the vast emptiness between galaxies, where there are almost no particles and very little radiation beyond that faint background, temperatures can approach this value. So space can get very close to the coldest limit possible, but it doesn't quite reach it. And more importantly, reaching that temperature is not about being surrounded by something cold. It's about having very little energy left. That distinction matters because it reinforces the idea that cold in space is not an active force. It's not something that presses in or surrounds objects. It's what remains when energy has been allowed to dissipate over time. Now, absolute zero also gives us a useful reference point. It tells us how far the process of cooling can go. If an object in space continues to radiate energy and receives no incoming heat, its temperature will drop, approaching that lower bound. But as it gets closer, the rate of cooling slows down. This is because the amount of energy being radiated depends on temperature. Warmer objects radiate more energy, cooling faster. Colder objects radiate less, cooling more slowly. So the closer you get to absolute zero, the slower the process becomes. It's like approaching a destination that keeps getting harder to reach the closer you get. You can get very close, but never quite arrive. This is why absolute zero is often described as unattainable. Not because it's forbidden in a dramatic sense, but because the process of removing energy becomes less and less effective as you approach it. Now, on Earth, reaching temperatures close to absolute zero requires very controlled conditions. Scientists use specialized equipment to cool materials to extremely low temperatures, often fractions of a degree above absolute zero. These environments are carefully isolated, designed to minimize any incoming energy and allow precise control over the system. In space, the situation is different. There is no laboratory, no controlled setup. But there is something else. There is time. Given enough time, and in regions far from stars and other heat sources, objects can cool down naturally, approaching the temperature set by the cosmic microwave background. This makes deep space one of the coldest natural environments in the universe. But again, it's not because space is actively cold, it's because there is so little energy present. Now, there's another interesting aspect to absolute zero. As temperatures approach this limit, the behavior of matter begins to change in ways that are not obvious from everyday experience. Materials can enter new states, where their properties become quite different. For example, certain substances can become superconductors, allowing electricity to flow without resistance. Others can form what are known as Bose-Einstein condensates, where particles behave collectively, almost as if they were a single entity. These phenomena occur because the usual thermal motion that separates particles is reduced, allowing quantum effects to become more prominent. While these states are typically created in laboratory conditions, they remind us that temperature is not just about how hot or cold something feels, it shapes the behavior of matter itself, and at very low temperatures that behavior can become quite unusual. Now, bringing this back to space, it's important to remember that while space can be very cold, it is rarely uniform. Even in regions that are close to the cosmic background temperature, there can be variations. A passing photon, a distant source of radiation, a nearby object, all of these can introduce small amounts of energy. So while absolute zero provides a theoretical limit, the universe as we observe it always has some level of activity, some motion, some energy. And that means that even in the coldest regions, there is never complete stillness. There is always something happening, even if it's incredibly subtle. This ties back to the broader idea we've been building. Cold, in the context of space, is not a single, simple condition. It's the result of energy gradually dispersing, of motion slowing, of systems moving toward lower energy states. And absolute zero represents the endpoint of that process, the boundary beyond which we cannot go. Somewhere far beyond anything we've ever directly experienced, there are regions of the universe where temperature drops to levels that feel almost difficult to describe in everyday terms. Not just cold in the sense of a winter night, or even the deep cold of space we've already talked about, but places where energy is so scarce that motion itself is barely present. And yet, these places don't exist because something is actively freezing them. They exist because almost nothing is happening at all. To begin understanding where the coldest places in the universe are, it helps to follow the same idea we've been building from the start. Temperature is not a force. It is not something that moves around on its own. It is a measure of how much energy is present, how much motion exists at the smallest scales. So if you want to find the coldest places, you don't look for something that removes heat aggressively. You look for places where heat has simply not arrived, or where it has been allowed to drift away for an incredibly long time without being replaced. One of the first candidates might seem obvious: deep space, far away from stars, galaxies, and any significant sources of radiation. Regions where there are very few particles, very little interaction, and almost no incoming energy. In these vast stretches between galaxies, temperatures approach that faint baseline set by the cosmic microwave background, around 2.7 Kelvin. That's already extremely cold. But interestingly, it's not the coldest, because even that background radiation provides a small amount of energy, a kind of universal floor that most of space rests upon. To find temperatures even lower than that, you have to look in more unusual places. Places where specific conditions allow energy to be reduced even further. One such place exists within our own galaxy, and it's known as the Boomerang Nebula. This region has been measured at about 1 Kelvin, even colder than the cosmic microwave background. At first, that might seem puzzling. How can something be colder than the general temperature of the universe around it? The answer lies in how the nebula behaves. The Boomerang Nebula is a cloud of gas expanding very rapidly outward. As it expands, the gas does work on its surroundings, and in doing so, it loses energy. This process causes it to cool. It's similar in principle to how expanding gas cools in certain processes we observe on Earth, though on a much larger and more extreme scale. As the gas continues to expand, it becomes less dense, and its internal energy decreases. This allows it to drop below the temperature of the surrounding background radiation. So instead of being warmed by the universe, it effectively cools itself through expansion. This is a rare and specific set of conditions, but it shows that temperature in the universe is not fixed. It can vary depending on how energy is transferred and transformed, and in this case, it leads to one of the coldest known natural places. But even that is not the end of the story, because the coldest temperatures we know of have actually been created on Earth. In laboratory settings, scientists have managed to cool small systems to fractions of a degree above absolute zero, far colder than anything naturally occurring in space. These experiments use precise techniques to remove energy from particles, often involving lasers, magnetic fields, and carefully controlled environments. In some cases, temperatures have been brought down to billionths of a degree above absolute zero. These are not places you can visit or environments that exist on a large scale. They are tiny controlled systems, isolated from external influences. But they demonstrate something important. Absolute zero is not just a theoretical concept. It is a boundary that we can approach very closely under the right conditions, and in doing so, we see how matter behaves when energy is almost entirely absent. Now, returning to the broader universe, there are other regions where temperatures can be extremely low, though not quite as low as these laboratory extremes. Dense clouds of gas and dust far from stars can cool to very low temperatures. In these regions, the lack of incoming radiation and the ability to radiate energy away allows temperatures to drop significantly. These cold clouds are often the birthplaces of stars, and this might seem counterintuitive at first, cold regions leading to the formation of stars, but the connection lies in density. As gas cools, it loses energy and can begin to collapse under its own gravity. This collapse leads to increasing density and eventually the conditions needed for star formation. So cold in this context is not just an end state, it is part of a process, a stage in the evolution of matter in the universe. There are also regions in space that remain in permanent shadow, similar to what we discussed on the Moon, but on a larger scale. Certain areas near the poles of planets or moons never receive direct sunlight. These regions can remain extremely cold for long periods because they are not exposed to incoming energy and continuously lose heat through radiation. While these are not the coldest places in the universe, they provide a more accessible example of how temperature behaves when sunlight is absent. Again, the pattern is the same: no incoming energy, continuous radiation, gradual cooling, and over time, very low temperatures. Now, when we talk about the coldest places, it's easy to focus on the numbers 1 Kelvin, 2.7 Kelvin, fractions of a degree above absolute zero. But those numbers, while precise, don't fully capture what's happening. Because at these temperatures, the concept of cold is no longer about sensation. It's about the near absence of motion. Particles moving very slowly, energy spread so thinly that it barely registers, and yet, even in these conditions, there is still activity, still motion, still energy, because absolute zero remains just out of reach, and this is an important point to carry forward. The universe, no matter how cold it becomes in certain regions, is never completely still. There is always something happening, even if it's incredibly subtle, even if it's almost impossible to detect without specialized instruments. So the coldest places in the universe are not defined by something freezing everything in place. They are defined by how little energy is present, how slowly things move, how quiet the system becomes, and that quietness is not emptiness. It's a state of minimal activity. A balance reached after energy has been allowed to disperse over vast distances and long periods of time. There's a point where the idea of temperature begins to feel a little detached from everyday experience, and that point usually arrives when we start talking about black holes. Up to now, temperature has been something we could relate to motion, to particles, to energy moving through matter or radiation. Even in space, where things behave differently, we've still been able to connect temperature to something physical, something that exists and can be measured in a familiar way. But black holes introduce a situation where the usual intuition starts to slip, because a black hole at first glance doesn't seem like something that should have a temperature at all. It doesn't have a surface in the normal sense. It doesn't contain matter in a way we can observe directly. It doesn't emit light in the way stars do. In fact, it's defined by the fact that not even light can escape from it once it crosses a certain boundary. So where would temperature even come from? And yet, surprisingly, black holes do have a temperature. Not in the way a warm object has a temperature, but in a more subtle, almost indirect sense. To understand this, it helps to start with what a black hole actually is, not in dramatic terms, but in simple physical ones. A black hole forms when a large amount of mass is compressed into a very small region of space. The gravity becomes so strong that it curves space and time to an extreme degree. At a certain boundary, called the event horizon, the escape velocity exceeds the speed of light. Anything that crosses that boundary cannot return. From the outside, this makes the black hole appear completely dark. No light escapes, no information comes out, and it seems, at first, like a one-way system. Matter goes in, but nothing comes out. If that were the whole story, black holes would not have a temperature. Temperature, as we've been describing it, is tied to energy exchange. It involves emission, absorption, and interaction. But black holes for a long time were thought to do none of those things. Then, something unexpected happened in theoretical physics. In the 1970s, Stephen Hawking showed that when you consider quantum effects near the event horizon, black holes are not entirely black. They can emit radiation. This radiation, now known as Hawking radiation, arises from quantum fluctuations near the event horizon. Without going too deep into the mathematics, the idea is that pairs of particles can form near the boundary, and under certain conditions, one of those particles can escape while the other falls in. To an outside observer, this looks like the black hole is emitting particles, and if something emits radiation, it has a temperature. This is where the concept of black hole temperature comes from, but it's not what we would normally think of as heat. There's no surface you can touch, no warm glow, no direct sensation. The temperature is a property of the radiation being emitted, a reflection of how energy is being released from the system, and here's where it becomes even more interesting. The temperature of a black hole depends on its size. Larger black holes are colder, smaller black holes are hotter. This is the opposite of what we might expect, but it follows from the way Hawking radiation works. A very large black hole, like the ones found at the centres of galaxies, has a temperature that is incredibly low, far below the temperature of the cosmic microwave background. In practical terms, this means it absorbs more energy from its surroundings than it emits. It is colder than the universe around it. A smaller black hole, on the other hand, would have a higher temperature and would emit more radiation. As it loses energy through this radiation, it would gradually shrink, and as it shrinks, its temperature would increase, leading to even more radiation. This creates a kind of feedback process where smaller black holes get hotter as they lose mass. But for most black holes we observe, especially the large ones, the temperature is extremely low, so low that it's almost negligible compared to other sources of energy. Now, what does this mean in terms of our broader understanding of temperature in space? It shows that temperature is not just about matter or even radiation in the usual sense. It can emerge from the structure of space itself, from the way gravity and quantum effects interact. A black hole, which we might think of as a region of nothingness, still has a temperature. Not because it contains particles moving in the usual way, but because it participates in a subtle exchange of energy with its surroundings. This challenges the idea that temperature always requires a tangible substance. Instead, it suggests that temperature is tied more fundamentally to energy and its behaviour, even in extreme conditions. It also reinforces something we've been seeing throughout this journey. Cold, in the universe, is not always about the presence of something cold. It's often about the absence of energy, or the way energy is distributed. Black holes, especially large ones, represent some of the coldest objects in the universe, not because they freeze things, but because they emit so little energy compared to their surroundings. They sit quietly, absorbing more than they give off, existing in a kind of thermal stillness relative to the rest of the cosmos. And yet, even they are not completely inactive. There is always that faint emission, that slow release of energy, governed by the laws of quantum mechanics. So even in one of the most extreme environments imaginable, there is no absolute stillness, no complete absence of activity, just a very subtle, very slow process unfolding over time. As this idea settles in, it connects back to everything we've been building. Temperature is not a simple property. It is not just hot or cold. It is a reflection of energy, motion, and interaction, whether those interactions involve particles, radiation, or even the fabric of space itself. And in the case of black holes, it becomes something even more abstract, a measure of processes that are not directly visible, but still very real. Far away from stars, far beyond the gentle reach of their light, there are regions of the universe where very little happens at all. Not in a dramatic sense, not as some kind of sudden emptiness, but as a gradual thinning out of everything. Fewer particles, fewer interactions, fewer sources of energy. The kind of place where distances stretch so far that even light takes years, sometimes thousands of years, to travel from one point to another. This is interstellar space. And if there is any place that comes closest to what we casually imagine as true cold, it would be here. But even here, the idea needs a little adjustment. Because what makes interstellar space so cold is not that something is actively freezing it. It's that almost nothing is there to keep it warm. To begin with, it helps to picture what exists between the stars. It's not completely empty. There are atoms, mostly hydrogen, drifting slowly. There are small amounts of dust, tiny particles scattered across vast distances. There are faint traces of radiation, including that persistent background glow we talked about earlier. But the density is incredibly low. In some regions, you might find only a few atoms in a space the size of a cubic centimetre. Compared to Earth's atmosphere, which contains billions upon billions of particles in the same volume, this is almost nothing. And with so few particles, interactions become rare. Heat, as we've been describing it, depends on interactions. It depends on particles exchanging energy, colliding, transferring motion from one to another. In interstellar space, those interactions happen so infrequently that energy is not easily shared. So if something has heat, it tends to keep it until it slowly radiates it away. And if something lacks heat, there is very little incoming energy to change that. This creates conditions where temperatures can remain very low for long periods of time. Now, the baseline temperature in these regions is still influenced by the cosmic microwave background, that faint glow at about 2.7 Kelvin. So even in the deepest parts of interstellar space, temperatures rarely fall below that level naturally. But what makes these regions feel like a deep freeze is the combination of low temperature and isolation. There is almost no energy coming in, almost no particles to interact with, and a continuous slow loss of energy through radiation. Imagine placing an object in such a region. At first, it might have some internal energy, some warmth, but with no surrounding medium to carry heat back to it, and no nearby sources of radiation. That energy would begin to drift away, slowly, steadily, until it approaches that background temperature. And once it reaches that point, it stays there. Not because something is holding it at that temperature, but because there is a balance between the tiny amount of incoming background radiation and the energy being radiated away. It's a kind of equilibrium, but a very quiet one. Now, there's something else about interstellar space that makes it particularly interesting. Time behaves differently there, not in the relativistic sense, but in the way processes unfold. On Earth, changes happen quickly because interactions are constant. Heat moves rapidly, energy is exchanged continuously, and systems evolve at a noticeable pace. In interstellar space, everything is slower. With fewer interactions, processes take longer. Cooling takes longer. Heating takes longer. Even chemical reactions, when they happen, can take vast amounts of time. So the deep freeze is not just about temperature, it's about stillness. Not complete stillness, but a significant reduction in activity. Particles drifting rather than colliding. Energy spreading out rather than concentrating. This gives interstellar space a kind of quiet persistence. Conditions remain stable not because they are actively maintained, but because there is very little to disturb them. Now, it's also important to note that not all interstellar space is the same. There are regions where gas and dust become more concentrated, forming clouds that can be the starting point for new stars. In these regions, temperatures can still be very low, but the increased density allows for more interactions. Over time, gravity can pull these clouds together, increasing density and eventually leading to the formation of stars. So even in the coldest parts of space, there is potential for change. Cold does not mean inactive, it means low energy. And given enough time, even low energy systems can evolve. But in the vast stretches between those regions where density remains low and energy sources are distant, the conditions remain remarkably consistent: cold, quiet, and persistent. Now, if we return to the question of how cold space really is, interstellar space gives us one of the clearest answers. Not because it is the absolute coldest, but because it represents the most natural widespread state. A place where energy is minimal, interactions are rare, and temperature is defined by the faintest background radiation. It is not a place that actively cools things down. It is a place where warmth has already faded, and where, in the absence of new energy, that condition continues indefinitely. This also helps explain why space does not feel like a freezer. A freezer is active. It uses energy to remove heat quickly, maintaining a low temperature environment. Interstellar space does not do that. It does not actively remove heat. It simply allows heat to leave without replacing it. And over time, that leads to very low temperatures, but always through a process, always gradually, always quietly. As this becomes clearer, the idea of cold in the universe shifts again. It becomes less about extremes and more about absence, less about force and more about balance. Try to imagine a place where almost nothing changes, not because everything has stopped completely, but because change happens so slowly that it becomes difficult to notice. Movements are subtle, interactions are rare, and energy is spread so thinly that very little seems to be happening at all. In environments like that, a natural question begins to form. If everything is moving more slowly, if processes take longer, if energy is reduced to such a low level, does time itself feel different? Not in the strict physical sense, where time is measured by clocks and defined by equations, but in the way time is experienced. Because there is a difference between time as a measurable quantity and time as something we feel. On Earth, our experience of time is shaped by change. We notice time passing because things happen. The movement of the sun across the sky, the ticking of a clock, the rhythm of our own bodies, all of these provide reference points. They create a sense of progression, a sequence of events that we interpret as time moving forward. But what if those reference points were reduced? What if changes became less frequent, less noticeable? In extremely cold environments, especially those in deep space, this is exactly what happens. At very low temperatures, particles move more slowly, chemical reactions take longer, systems evolve at a reduced pace. Everything continues to function according to the same physical laws, but the rate at which things happen decreases. And while this does not change time itself, it changes the density of events within a given period. Fewer interactions, fewer changes, fewer markers to measure the passage of time. If you were observing such an environment, it might feel as though time was stretched, not because time itself has slowed, but because there is less happening within each moment. This is similar in a way to experiences we have in everyday life. When you are engaged, when events are happening quickly, time can feel like it passes rapidly. When you are waiting, when very little is changing, time can feel slow. The clock ticks at the same rate in both cases, but the experience is different. Now extend that idea to an environment where change itself is reduced at a fundamental level. In interstellar space, where temperatures are low and interactions are rare, processes can take incredibly long periods of time. A cloud of gas might take millions of years to collapse into a star. A chemical reaction that would occur quickly on Earth might take thousands of years. From an external perspective, time is flowing as it always does, but from within that system, the pace of events is very slow. So the feeling of time, if it could be experienced, would be different, more stretched out, more sparse. This leads to an interesting distinction. Time as measured by physics remains constant in these conditions, at least in the absence of relativistic effects. but time as experienced is tied to change, and when change is reduced, the experience of time shifts. Now, it's important to separate this from the effects described by relativity. In extreme gravitational fields or at very high speeds, time itself can be measured to pass at different rates, relative to different observers. That is a physical effect, something that can be calculated and observed. What we are discussing here is different. It's about perception, about how the density of events shapes our sense of time. In extremely cold environments, the slowing of processes creates a kind of sparsity. Events are spread out over longer intervals. There is less happening per unit of time, and this can create the impression of time being slower, even though the underlying flow of time has not changed. Another way to think about it is to consider motion. If you watch something moving quickly, you can easily track its progress. If it moves very slowly, its change becomes harder to notice. If it moves slowly enough, it might appear almost still. In extremely cold environments, where particle motion is reduced, many processes approach that level of subtlety. Changes are still occurring, but they are less apparent. And without frequent changes to mark the passage of time, the experience of time becomes less defined. Now, if we bring this back to the human perspective, it becomes even more interesting. Our sense of time is closely linked to our internal processes. Our heartbeat, our breathing, our thoughts, all of these create a rhythm. They provide a steady stream of events that help us track time. In a cold environment, the body's processes would slow down, though not in a way that would stop them entirely. Metabolic rates can decrease in certain conditions, reducing the rate at which energy is used. This is something we see in hibernating animals, for example, where activity levels drop and bodily functions slow. In such states, time can feel different. Not because time itself has changed, but because the internal markers we rely on have shifted. Now, space introduces additional complexities, but the principle remains. The experience of time is tied to change, both external and internal. When those changes become less frequent, less intense, or more spread out, the perception of time adjusts accordingly. So in extremely cold environments, especially those with very low levels of activity, time might feel more extended. Moments might seem longer, not because they contain more time, but because they contain fewer events. This is a subtle effect, but it connects back to the broader theme we've been exploring. Temperature, energy, and motion are all linked. As energy decreases, motion slows. As motion slows, change becomes less frequent. And as change becomes less frequent, the way we perceive time can shift. But throughout all of this, the underlying flow of time remains the same. It continues, steady and constant, regardless of how much or how little is happening. This brings us to an interesting conclusion. Cold does not change time itself. It changes the pace of processes within time, and it is that change in pace that can alter the experience of time. So when we imagine the coldest parts of the universe, we're not just imagining low temperatures. We are imagining environments where activity is reduced, where motion is minimal, and where change unfolds slowly. Places where time is not different, but where everything that happens within it takes its time. There's a quiet pattern that begins to emerge once you've spent a little time thinking about how temperature behaves beyond Earth. It's not something dramatic or immediately obvious, but it shows up again and again if you look closely enough. The farther something is from a source of energy, the colder it tends to be, and the less light it receives, the less heat it has to work with. This connection between cold, darkness, and distance is not a coincidence. It's built directly into how energy moves through the universe. But to really understand why these three ideas are so closely tied together, it helps to take a step back and look at what light actually is. Light is not just something that allows us to see, it's a form of energy. When light reaches an object, it carries energy with it, and when that energy is absorbed, it increases the motion of particles within that object. That increase in motion is what we measure as temperature. So when an object is exposed to light, especially strong light like sunlight, it gains energy and warms up. When that light is absent, when the object is in darkness, there is no incoming energy from that source. And without incoming energy, the only thing left is outgoing energy. The object continues to radiate heat away, as all objects do, but nothing replaces it. So over time it cools. This is the simplest version of the relationship. Light brings energy in, darkness removes that input, and distance determines how much light actually arrives in the first place. Now, distance plays a particularly important role because of how light spreads out. As light travels away from a source, it spreads over a larger area. This means that the farther you are from that source, the less energy you receive per unit area. It's not that the source becomes weaker, but that its energy is distributed more thinly. You can think of it like this. Imagine standing close to a fire. The warmth is strong and immediate. Step back a little, and the warmth is still there, but less intense. Move farther away, and eventually the warmth becomes barely noticeable. The fire hasn't changed. Your distance from it has. The same principle applies to stars. The sun, for example, provides a significant amount of energy to Earth because we are relatively close to it. That energy is enough to warm the surface, drive weather patterns, and support life. But as you move farther away from the sun, the amount of energy reaching any given point decreases. Planets farther out receive less sunlight and are generally colder. Move beyond the planets into the outer regions of the solar system, and the energy from the sun becomes weaker still. And beyond that, in interstellar space, the influence of any single star becomes minimal. Distance reduces the intensity of incoming energy. Darkness is what remains when that energy is no longer present, and cold is the result of that absence. Now, it's important to remember that cold itself is not something that travels or spreads in the way light does. Light carries energy outward. Cold is simply what we observe when energy is low. So when we say that darkness is cold, what we really mean is that darkness lacks incoming energy. There is no light bringing heat. And without that input, objects lose energy through radiation, gradually, steadily. This is why shadows are colder than areas exposed to sunlight, even on Earth. In sunlight, energy is constantly arriving, warming surfaces. In shadow, that input is reduced or absent, so surfaces cool. On Earth, the atmosphere softens this effect. Light is scattered, heat is distributed, and the difference between light and shadow is moderated. In space, without an atmosphere, the difference becomes much sharper. A surface in direct sunlight can be very warm. A surface in shadow can be very cold, and the transition between the two can be abrupt. This is one of the reasons why darkness in space is often associated with extreme cold. Not because darkness itself is doing something, but because it represents a lack of energy input. Now, distance amplifies this effect on a larger scale. The farther you move from a source of light, the less energy you receive, even if you're not in complete darkness. So cold is not just tied to darkness, but also to how far you are from energy sources. In the outer regions of the solar system, for example, sunlight is still present, but much weaker. Temperatures are lower not because space is inherently colder there, but because less energy is arriving. And in the vast spaces between stars, where light from any single source is extremely faint, the overall energy level is very low. This creates the conditions we associate with the deep freeze of space. But again, it's not a force, it's a condition, a result of low energy density. Another way to look at this is to think about balance. An object's temperature is determined by the balance between energy coming in and energy going out. On Earth, this balance is influenced by the atmosphere, by weather, by the presence of water, and by many other factors. In space, the balance is simpler. Energy in comes primarily from radiation, from stars or other sources. Energy out leaves through radiation. If the incoming energy is high, the object warms, If the incoming energy is low, the object cools. Distance reduces incoming energy. Darkness removes it entirely. So both contribute to cooling. Now, there's also something interesting about how our perception ties into this. We tend to associate darkness with cold because of our experiences on Earth. Night is cooler than day. Shaded areas are cooler than sunlit ones. These patterns reinforce the connection in our minds. But in space, the relationship is more direct. Darkness means no incoming light. No incoming light means no added energy. And without added energy, objects cool. There is no atmosphere to complicate the picture. No scattering, no redistribution. Just a direct link between light, energy, and temperature. This is why regions of space that are shielded from light for long periods can become extremely cold. It's also why objects that move into shadow begin to cool, even if they were previously warm. The absence of light immediately changes the balance of energy, and because there is no air to slow down the process, the effects are more pronounced. Now, if we extend this idea even further, it helps explain something about the structure of the universe itself. Stars are sources of energy. They emit light, which carries heat outward. Planets and other objects absorb that energy and radiate it away. As you move farther from stars, the influence of that energy decreases, so the universe, on average, becomes colder as you move into regions with fewer energy sources. This creates a kind of gradient, not a sharp boundary, but a gradual shift, from regions of higher energy to regions of lower energy, from light to darkness, from warmth to cold. And this gradient is not imposed by anything external. It arises naturally from how energy spreads and dissipates over distance. Now, bringing this back to the central idea, the connection between cold, darkness, and distance is not just a coincidence. It is a direct consequence of how energy behaves. Light carries energy. Distance spreads that energy out. Darkness represents the absence of that energy, and cold is what remains when energy is low. So when we imagine the coldest parts of the universe, we're often imagining places that are both far from energy sources and shielded from light. Places where incoming energy is minimal and outgoing radiation continues. Places where the balance tips toward cooling. And over time, that leads to very low temperatures, but always through the same process. Not freezing, not sudden change, just a gradual reduction in energy. There's a moment, usually quiet and familiar, when you step outside on a cold day and immediately know how it feels. Not because you measured the temperature, not because you calculated anything, but because your body tells you. Your skin tightens slightly, the air feels sharper. You might pull your hands closer or adjust your posture without even thinking about it. It's an instant interpretation, something built from experience rather than calculation. And yet, if you pause for a second and look at what's actually happening, something interesting begins to appear. What you feel as cold is not the same thing as what physics describes as low temperature. Those two ideas are connected, but they are not identical. And once you begin to separate them, the way we think about cold, especially in space, starts to shift again. To begin with, the human experience of cold is based on change. More specifically, it's based on how quickly your body's losing heat. If heat's leaving your body rapidly, you feel cold. If heat is leaving slowly, you might feel comfortable, even if the actual temperature is low. So the sensation of cold is not just about temperature itself, it's about heat flow. This is why a metal surface can feel colder than a wooden one, even if both are at the same temperature. The metal conducts heat away from your skin more efficiently, so your body loses heat faster, and that creates a stronger sensation of cold. The wood, by comparison, slows that transfer, so it feels warmer. Your body is not directly sensing temperature. It is sensing the rate at which energy is being transferred. Now think about how this applies to air. Cold air feels cold because it carries heat away from your skin. If the air is moving, like in a wind, that process becomes even more efficient, and the sensation of cold increases. This is what we call wind chill. The temperature hasn't necessarily changed, but the rate of heat loss is increased, and your body interprets that as cold conditions. So from the human perspective, cold is closely tied to interaction. Air moving across your skin, surfaces in contact with your body, heat being transferred away. Without those interactions, the sensation of cold changes. Now consider space. In space there is no air, no wind, no medium to carry heat away through convection, and very little direct contact with anything. So even though the temperature of space is extremely low, the mechanisms that create the sensation of cold are largely absent. Heat still leaves your body, but it does so through radiation, which is a slower process. There is no cold air rushing past you, no immediate transfer of heat through contact with the surrounding medium. So the experience of cold, if it could be felt in the same way, would be very different. Not an instant chill, not a sharp sensation, but a gradual loss of warmth. This is one of the key differences between the human experience of cold and the physics of cold. Physics describes temperature as a measure of energy. The human body interprets cold as a rate of energy loss. These are related but not the same, and this difference explains why many of our intuitions about space don't quite match reality. We imagine space as something that would feel intensely cold immediately because we associate low temperature with strong sensation. But in reality, without the mechanisms that create that sensation, the experience would not match the expectation. Now, this doesn't mean space is safe or comfortable. It simply means that the way temperature affects the body is different from how we might imagine. The body would still lose heat over time, internal processes would still be affected, but the initial sensation would not be the same as stepping into freezing air on Earth. It would be quieter, less immediate, more subtle. Another important aspect is how the body regulates temperature. On Earth, the body uses a combination of mechanisms to maintain a stable internal temperature. It can produce heat through metabolism. It can conserve heat by reducing blood flow to the skin. It can release heat through sweating and increase circulation. All of these processes depend on interaction with the environment. Sweating relies on evaporation, which depends on air. Heat loss through the skin depends on the surrounding temperature and the movement of air or water. In space, many of these processes become less effective. Sweating does not work in the same way without air to carry moisture away. Heat loss through convection is absent, so the body's ability to regulate temperature is altered. This creates a situation where internal control becomes more important, but also more limited. The body is still generating heat, but the ways it can lose that heat are reduced. At the same time, it is still radiating energy outward. So again, it becomes a balance. Energy produced internally, energy lost through radiation, and without the usual pathways, that balance behaves differently. Now there's also a psychological component to how we experience cold. Our perception is influenced by expectation, by context, and by comparison. A temperature that feels cold in one situation might feel comfortable in another, depending on what we're used to. This means that cold is not just a physical condition, it is also an interpretation. In space, where many of the usual cues are absent, that interpretation would be different. There would be no wind to signal cold, no air to create that immediate sensation. So the experience would be less about feeling cold and more about noticing changes over time. A gradual shift rather than an instant reaction. This distinction becomes especially important when we try to imagine environments that are very different from Earth. It reminds us that our senses are tuned to specific conditions. They evolved in an atmosphere, with air, with pressure, with constant interaction. When those conditions change, the way we perceive things changes as well. So when we talk about the cold of space, we have to be careful not to project our Earth-based experiences directly onto it. The physics is clear: low energy, slow motion, gradual heat loss. But the human experience, if it could occur in such an environment, would not match the familiar sensation of cold we know. It would be shaped by different mechanisms, different rates of energy transfer, different interactions, or the lack of them. And this brings us back to the central idea. Cold, as a physical concept, is about energy. Cold, as a human experience, is about how that energy moves in and out of our bodies. In space, those two perspectives diverge. The physics remains the same, but the experience changes, and understanding that difference helps us build a clearer picture of what space is actually like. Not just cold in a simple sense, but complex, subtle, and shaped by the absence of the very things we rely on to feel temperature at all. Take a moment to let everything settle, not in a dramatic way, not as a conclusion that closes things off, but simply as a quiet pause where all the pieces we've been exploring begin to sit together more clearly. Because by now, the idea of space being cold has changed quite a bit. At the beginning, it might have felt like a simple question. How cold is space? A number, perhaps, a comparison, something you could describe quickly and move on from. But as we've moved through it, layer by layer, that simplicity has softened. Cold is no longer just a number. It's a process. It's a balance. It's something that unfolds over time, rather than something that arrives all at once. And more importantly, it's something that depends on energy, not on an environment pressing in around you. That distinction has been there from the start, quietly shaping everything else. On Earth, cold feels immediate because we are surrounded by air. Heat is constantly being carried away from us, transferred through contact, through movement, through interaction. The sensation is direct, noticeable, and often sharp. In space, that surrounding medium is gone. There is no air to carry heat away, no wind to create a chill, no continuous exchange that forces everything toward the same temperature. Instead, each object exists more independently, gaining energy from radiation, losing energy through radiation, and settling into a balance that depends entirely on its own circumstances. And because of that, cold becomes quieter. Not weaker, not less real, but less immediate, less forceful, more gradual. You've seen this in how heat leaves objects in space, slowly drifting outward rather than being pulled away. You've seen it in how sunlight can heat one side of an object while the other side cools at the same time. You've seen it in the moon's long cycles of heating and cooling, and in the way spacecraft have to manage their own temperature because nothing else will do it for them. You've even seen it in how the human body would respond, not with an instant freeze, but with a gradual shift, shaped by the absence of the very mechanisms that normally define how we feel temperature. And then there's that faint background, the quiet glow left over from the early universe, setting a kind of baseline, a reminder that even in the emptiest regions there is still a trace of energy. Not much, but not nothing. All of these pieces point toward the same idea. Space is not actively cold. It is passively allowing heat to leave. And over time that leads to very low temperatures, but always through a process, always gradually. Now, if you step back and look at the larger picture, something else begins to stand out. Cold, in the universe, is often tied to absence. The absence of nearby stars, the absence of light, the absence of dense matter. The farther you move from sources of energy, the less energy there is to absorb, and the more objects rely on their own internal energy, slowly radiating it away. This is why interstellar space feels like a deep freeze. Not because something is freezing it, but because there is so little energy present. It's also why darkness and distance are so closely linked to cold. Light carries energy. Distance spreads that energy thin. Darkness represents the absence of incoming energy, and cold is what remains when energy is low. Even in the most extreme cases like black holes, where temperature takes on a more abstract meaning, the same principle applies. Temperature is tied to energy and how it is exchanged. Even in places where matter behaves in unfamiliar ways, that connection remains. And then, at the far edge of this idea, there's absolute zero. Not a place, not something you can reach, but a limit. A boundary that tells us how far the process of cooling can go. A point where motion is reduced as much as possible, where energy is minimized but never completely gone. Because even in the coldest conditions, there is always some motion, some activity, some trace of energy. That too is part of the picture. The universe is never completely still. Now, bringing all of this together, the question we started with begins to feel different. How cold is space, really? The answer is not just a number, it's an understanding. Space can be extremely cold, close to just a few degrees above absolute zero in many regions. But that cold is not something that rushes in or surrounds you in the way we might imagine. It's the result of energy slowly dispersing, of motion gradually decreasing, of systems settling into lower energy states over vast stretches of time. It's quiet, it's patient, it's steady. And in a way, it reflects something broader about the universe itself, the way things evolve, not through sudden changes, but through gradual processes that unfold over long periods. Now, as you think about that, it might be worth returning to where you are right now. Whatever temperature you're in, whatever environment surrounds you, there's a constant exchange happening. Air moving, heat transferring, energy flowing in and out, all of it shaping your experience of warmth or cold in ways that feel immediate and familiar. And just beyond that, beyond the atmosphere, beyond the layers that make Earth feel the way it does, there's a different kind of environment, one where those exchanges are reduced, where heat leaves more quietly, where temperature is defined less by sensation and more by balance. It's not something you feel directly, it's something you understand. And as that understanding settles in, the image of space becomes a little clearer. Not an endless freezer, not a place of instant extremes, but a vast quiet environment where energy moves slowly, where warmth fades gently, and where cold is simply what remains when there is very little left to move at all. And with that in mind, you can let the idea drift a little, just like heat does in space, not disappearing, but spreading out, becoming softer, less defined, and a bit easier to rest with as everything continues slowly and steadily, just as it always does.